Hey guys, Friday, December 2nd. Uh, so I'm in an empty classroom right now. We actually got a pretty good recording in class, but well, or I thought we did. I went and checked my computer and I don't know, it didn't record. I remember very clearly it was recording. And I don't know what happened. So I'm gonna try to sort of recreate what we did in class. So you guys have a video for today. Okay, so uh, one thing going on is about a third of the class is going to be out on Monday for an FCLE exam. So I told you guys, and you guys told me that you would rather push the AP classroom off to Wednesday. So I have, in the meantime, gone ahead and bumped the due date to Wednesday morning. So I'll do some activity with you guys on Monday, probably an FRQ, maybe one or two other things. We're going to do rotational inertial lab. We'll do AP Classroom. We'll cover that on Wednesday. We'll have an in-class open notes rotational dynamics quiz on Thursday, and we'll start the midterm review on Friday. Have to go fix this over the weekend, prep some stuff for next week, but that's what I think we'll be looking at. Okay. We did a quick center of mass activity. So I have 9 different foam boards. This is one of them. This one's like a T-type shape. And I give you guys the multiple choice option for center mass. Now, this one happens to be option D is what the center mass is. And there are a few different ways you can find it. One way is you can bounce it down your finger at that point. Another way is you can clip these binder clips. So clip this binder clip anywhere around the perimeter. And then the other one's going to provide weight, and the string always hangs through the center mass, regardless of where you hang it from. A third way you can find center mass is if you threw this in the air and say like started like rotating as it was going through the air. If you clip an LED light like on the edge, it's going to look all spirally like it's going through the air. But if you put an LED right here at the center mass, that will make a nice smooth parabola as it's flying through the air. So there's a few different ways. All right, so you guys have these foam boards at your desk. I had you guys just do this as a small activity. All right, so got from on there. Then I did show you guys not the full videos, but a couple of video demos that are related to some rotational dynamics things that we're doing. There was a weird one with billiards balls. Steve Mold uploaded recently, so I will upload the link also to Google Classroom so you can access the whole thing if you want. And also there was a Pinewood Derby video from Mark Rover, who used to be a NASA scientist, now has a thriving YouTube channel. So this is a good recap of conservation of energy and also incorporates rotational motion. So Pinewood Derby car, this is a little car kit you can buy. It's about this big, and there's this wood body. You can cut it yourself and sand it down and paint it, and then put on the wheels and put on weights. Okay? And then they race these cars. And what factor? How can you win the race? Right? And there are a bunch of little factors you can change. So I went through. I just hit a couple of points in the video. It's really long one, so again, I'll upload that link to Google Classroom so you can access the whole thing. It's a really good one for this. But what we're looking at here is a really good framework to figure this out is conservation of energy. Right? And then once you have this framework, right, you have all the bits, then you have a really good bird's eye view of what things you could change to maximize your chance of winning this race. He goes through the video with this context, with this framework, and also get some empirical data and tell us how you do this. So I have an open system here, right? Sum of energy initial minus work done by friction equals the sum of energy final. See if it was a closed system, I might just say that. But open system, we have this going on, right? And say, okay, what kind of energy does it have at the very top? You guys told me in class, oh, it has potential energy, so call it MGH, right? Now, the work done by friction, if you want to get a little bit more specific, you could say that's some frictional force times the length or something like that. Okay? And the frictional force, I might call it coefficient of friction times the cosine component of the weight. Or at least that's traditionally how we do it. I guess if you really wanted, you could say, well, maybe it's some friction between the wheel and the axle, some version of that. But anyway, so some do like some kind of frictional loss. Right? And what kind of energy is going to have at the bottom? Well, it has no more potential energy because it's at the bottom, but it has energy of motion. So I could say kinetic energy, but really it's 2 kinds of kinetic energy. There's translational kinetic energy, your 1/2 mv squared. So if you point a radar gun at it, pick up its speed, right? That's what that V is. And then something to do with rotation. You can imagine it has like 4 wheels on it, right? And those could be rotating. So 1/2 I omega squared is an expression for rotational kinetic energy. So analogous to 1/2 mv squared, 1/2 I omega squared. And if each I could be like a wheel, individual wheel, okay. By the way, a wheel is approximately cylinder shaped. So you could probably estimate the rotational inertia of a wheel if you know with math and radial size, just this expression right here, 1/2 omega squared. Right. So if you want to go a step deeper with that. Okay. And then, hey, there are 4 wheels. So if this is for 1 wheel, you could just do 4 of those, right? You could do that. Then one of the things that he says in the video actually is one of the ways to win the race is to actually take one of the wheels and take one of the axles and bend it, or so that only 3 wheels left. Three wheels are actually making contact with the surface, so that only 3 wheels are rotating instead of 4. So there's like 1 dead wheel. And the advantage of that is this 4 changes to a 3, and now there's less energy that goes into making the wheels rotate, which means you have more energy left over, therefore to go into translational kinetic energy, more likely than 1 race. The cars that do that, that lift one of the wheels off and only have 3 wheels going down, those cars just always win the race. That's a really big advantage, right, in this type setup. The other connection I want to make is this V and this omega are related to each other, right? So how fast is the car going linear speed, how fast the wheels rotating. So that goes back to, pull this poster up here. This right here, right? They're related to each other by the radial size of the wheel in this case. So if you want to go ahead and solve the rest of this problem, one of the, say like solve for V in terms of, if you had everything else, one thing you have to do is substitute out one of these guys in terms of the other. So I might do like omega is equal to V divided by R, you divide this down and substitute that in right here, and then you could like solve for V, right? If you were trying to do that, right? Okay. So a problem that this is really similar to, that's one of my favorite problems in physics, is if you have a ball rolling down an incline, how fast is it going at the bottom? Okay. Now, important to note that this is rolling without slipping, so there is static friction. Now, if there was no friction at all, it would never even roll. It would just go down without rolling. It would look really weird, like a knuckleball. Right, so there has to be friction to induce rolling, and you specifically want static friction and not kinetic friction, so it's rolling without slipping. See, like if there's kinetic friction, it's like sliding along, then well, now you're back to having like some frictional losses. But if it's rolling without slipping, then that friction force is a conservative force. So like I had like a half pipe going up here, so like another. So if this ramp went down then back up, this bowling ball could just roll back and forth forever, right? That friction would not actually take any energy out of the system. So we got a conservation of energy setup. It's all potential energy at the top, right? MGH. Oh, by the way, H is equal to L sine theta, isn't it? This L is theta, right? We've done like hundreds of those by this point in this class. Right? And at the bottom, it's kinetic energy, which begins 2 types. You got your translational kinetic energy, like pointer radar gun at it, right? And also rotational kinetic energy, something to do with it rotating. And here's where the shape of the rolling object matters. The fact that it's a solid sphere for a bowling ball, right, tells you that this I would be 2 fifths mr squared. Right, I'm going to do some substitution here, right? Right? So from this line to this line, just do some substitutions. This H could be L sine theta if that's relevant, if you're given L and theta. Suppose you're solving for this V. Again, this, omega is related. Oh, look at that. Omega is V divided by R, just like I said for like before. It goes back to this right here, the little substitution. Okay. Then roll the object. Let's find. There we go. Here's the rotational inertia table. Here it is. All right. Here's my 2 fifths mr squared for the solid sphere. That's where. Okay. That's where the substitution came in because it's a solid sphere bowling ball. That's that. Okay. So then you could go ahead and do some more algebra and solve for V, if you were given everything else, or if you're solving in terms of variables, one way or the other. Okay. Now, show you guys a couple other perspectives on this, because the notes that I gave you guys back on Monday, there were a couple of printed slides that look really similar to, oh, whoops, I overshot it. Go back a little bit here. Where are my roller balls going down this incline? Here we go. Okay. So showed you guys a basketball. Now a basketball could be like a hollow sphere, which could have a different moment of inertia, right? And I gave you guys 2 perspectives on this. So there's the energy setup, kind of like I just took you guys through, okay? And there's also like a forces setup, just dynamics, right? Look at free body diagram forces, causes of torque, the whole deal, okay? Right. Notice that the forces acting on the ball, we got the weight treating as the acting at center mass. and the friction force acting at the edge, that's setting up a torque system to rotate all the way down. Okay. And so if you run the numbers on this, by the way, there's a typo in your guys' notes, so it should be a 6/5 here. This is just one of the middle steps. Okay. You can get the speed of the basketball at the bottom, which is this expression here. Notice that the mass and the radial size of the ball cancel out. So the square root 6/5 GH counts for anything that's a spherical shell. So if I put a ping pong ball next to the basketball, which same thing, it's just a spherical shell. Okay? I bet those would roll down side by side all the way down, ping pong ball and basketball. Just like a marble and a bowling ball, marble and a bowling ball are both solid spheres, would also roll side by side, jump all the way down. So the mass and the radial side cancel out. Okay? The other way, of course, you could do this is conservation of energy, which I think is actually an easier way to approach it. Okay, potential energy at the top, translational kinetic energy, rotational kinetic energy at the bottom. Okay, use some substitutions, blah, 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 you get the exact same answer. There you go. Okay, so one of my favorite physics problems there. Wait, forget if I emphasize this point. Let's go back to that roll race. Okay. Yeah, so all these rolling objects rolling down, right? It's really the distribution of mass going to determine who wins the race. Okay. So the frictionless lane air hockey puck is beat all of them. Now all these guys have static friction. Okay. And then the ring will always lose the race because it has the most rotational inertia. Next thing we did was we broke out these puzzles and I was guiding you guys through these. Okay, so I'll walk you guys through these here. We start with number 22, the hungry bear walking around out on this ledge. Now there's some forces going on with this this beam. Right now, this beam could pivot, okay? And there's a joint here. It's being pressed into the wall, and also it's being held up at the point of the wall. The bear has some weight, the beam has some weight, the basket of goodies has some weight, and this cable tension, there's some maximum tension it could go to. And as the bear walks to the right, you think the tension's going up, 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 up. And at some point, it maxes out the tension and it breaks. So the question is, how far can the bear walk out? Okay, so let's flip to that. All right. Just like we did in class. Here's the picture blown up. Okay. Easier to see right here. Okay. So the beam has a weight. We're going to treat acting at its own center mass. It's kind of distributed along the whole thing, but we'll treat it as acting at the center. Okay. Here's the bear. Okay. Here's the basket of goodies. Here's the tension in the rope, which you can split into components. There's a sine component and a cosine component if you're playing off this angle, which is equivalent to this angle. Okay. And see that the part pushing into the wall. Now, in terms of the force of summing to zero, it's going to balance out with the wall pushing back. Okay, but it doesn't actually cause any torque. Right? The part that causes torque is this component right here, just the vertical part of the full tension. Okay? Only that, right? The part that's 90 degrees to the beam. Okay? Okay, now, at the joint, right, there are two forces. There's the wall pushing the beam back in place, which is balancing this force, or this component. Right? So equal to each other. Okay? And also at the joint, it's holding up, right, helping the tension along here. Right now, as the bear walks from left to right, these forces are going to go like this, back to the left, back to the right, as the bear's walking. Okay? So how far out X can the bear walk? So here's your equilibrium conditions. The sum of the forces in the X direction is zero. That's these guys. The sum of the forces in the Y direction is zero. That's this stuff and this stuff has to balance with these three guys down. And the sum of the torque is equal to zero. Now, you guys remember from your lab that we did over 2 days, you can pick any point as like the pivot point to sum the torque about. Okay? But usually there are some points that are more opportune than others. I really like this point, not just that it's the most intuitive point to pick as the pivot point, but also because the fact that there would be 2 unknown forces here, if you pick that as your pivot point, each of those forces is causing zero torque about the point itself. Kind of like if you push on the hinges of a door, it'll never open the door. So bam, we just knocked out 2 unknowns if you set it up that way. Okay, so set up this expression right here and got this, right, and solve the tension that way. If you sum, all right, here, if you let the maximum tension go to this many newtons and you let the sum of the torque go to zero. Now this is force times lever arm, but let's check this out. So right, we have a 700 Newton bear at some distance x. 700 bear at some radial distance x that we're solving for. Okay? The weight of the beam we're going to have acting at the center, which is if the beam was 6 meters long, then halfway is 3 meters. Right? Oh, and then at the far end of the beam, at the full 6 meters, is the 80 Newton basket of goodies. Okay, it's like that. Okay, and then it's not the full tension, but the sine component of the tension. Also, it's the 6-meter M mark, right? That's pulling back. Right now, we're going to let that tension go to 900 newtons when it breaks, and solve for X. So you can solve this whole thing with just this torque setup, okay? And you should get this number. Okay. I assigned you guys this fridge. So there's a refrigerator on an incline. You're going to tip with the incline. At some point, the fridge is kind of topple over. And really what you're looking for is the center mass to leave the space of support. So it's just a pure geometry question. It's real fast right there. Okay, so that's that one. Okay. Then we looked at, well, I was going to say the rest of these, but I just realized we, this one. Okay, so I'll have to come back to number 63 next week. Although you guys have the solutions for that too. So, okay. So we looked at number 35, rope of negligible mass wrapped around a solid cylinder of given radius. Here, see if I have a picture of this. There, it looks like this. So we got a solid cylinder, there's a rope wrapped around, okay, and we're going to hang weight from it. They told you the mass of like some guy hanging. Okay, now you can get the weight by just do mass times gravity field, but that's actually not exactly equal to the tension force. You guys might remember like elevator physics from back in the day. See, like if you put a weight here and pull down, then the fact that this whole system is accelerating, the tension is actually a little bit less than the weight. Remember, it's like m times g minus a. Now, if you see this on AP, you have to derive this from scratch, but we've done this a few times in class in the past few months. So you can derive this. Okay. Now, in the past, we've had it where this pulley is like massless or approximately massless, which is a pretty good assumption if you have like this compared to this, right? But that's not true anymore. So starting with this chapter, say, well, what if this does have significant mass, right? So it has significant rotational inertia. In fact, for a solid cylinder, that'd be 1/2 mR squared, right? Straight off that table that we were looking at earlier. Okay. So this is one way to solve it. You can say this tension crossed with this radial force, so got a torque going on there, right? Remember, this tension is a little bit less than the weight, it's m times g minus a. That's equal to I times alpha, where I for the disk is 1/2 mR squared. We've got alpha. Now this alpha and this A are related to each other, right? Because alpha is equal to A over R. That's like this connection right here, right? So this rotating versus like a linear acceleration at the edge, that's the connection right there, right? So yeah, so once you got that all subbed in, then you can get this expression, then sub in values, and boom, there you go. Right? Or if you like, you could sub in the values to start them. All right, and then if you're solving for angular acceleration, you can just do it this way, or you can substitute it differently to start with from before. Okay. Number 52 is a pretty similar looking setup, right? You've got a bucket, a solid cylinder, it's rotating just like that. Look to this on the here. Okay. Oh, and it prompts you to use conservation of energy specifically, which I actually prefer to do myself because I really like this method. I think it's a really clean way to do this. Because at the top, the bucket has all potential energy, and that's it if it starts to rest. That's all the energy in the system. Okay. Then when the bucket falls, it's fallen some distance. Well, that energy is going to have gone into two places. The bucket itself has a linear speed and therefore a kinetic energy. And this disk right here has, the spool is going to have a rotational kinetic energy, 1/2 I omega squared. So here's the bucket, here's the spool. Okay. Is that what they're calling this thing? Yeah, the spool. Okay. So they might have different masses themselves. So this little mass and this big mass are different from each other. Okay. But again, this V and this omega are connected, right? They're connected just like this. So however fast the spool is turning and however fast the bucket's moving, those are connected just like this. Okay. By the radial size. Right. So you can make a substitution there. Okay. Once you have this set up and make these substitutions, then you get an expression that looks like this. You can solve for omega, which would be how fast is the disk rotating. Okay. Now this would be as a function of how far it's fallen. So this H, like at some point they say it's fallen 4 meters. Okay, so 4 meters. Okay. In fact, whenever you're given a setup like this and you're told how far it falls, conservation of energy is a really fast way to solve it. The other thing they could have said is like how much time it falls for. They could have said, oh, it fell for so many seconds, which notice they did not tell you. And then that'd be a few extra tricky steps. You could still use this method and go around that different way. Okay, right, but yeah, falling kite, here's bam, 4 meters is right there. Okay. You get how fast is it spinning, after the bucket has fallen that distance 4 meters. Okay. Okay, we got 2 more to go here. Yeah, I might come back to 63 on Monday, although you guys have this. Right. All right. Let's do 75 because I know I did that in class with you guys. 75. We've got this bar. It's got these springs at these locations, and they told you what 2 of these forces are reading, and they want to know 2 things. One is what is the third force, and the other thing is where would you put the spring for all those forces to play out exactly. And now there are 2 conditions you're looking for. One is that the forces in the y direction have to zero out. So these 2 upward forces, okay, and then the downward force from the spring. Oh, also the bar has some weight itself, right? Has to zero out. All those forces have to zero out, and you can solve for the magnitude of this force. Now, this only works at one specific location, and you can determine that location by applying torque. The sum of the torque goes to 0. So I've got, you can pick any point as the pivot point, but say you pick the far left point, for example. Okay, here it is. Here's the setup. So 0 torque is caused by this force that we just found at this distance x that we're solving for. Okay. That's clockwise relative to this point. The weight of the bar itself is causing a clockwise torque, and the F2 on the far end is causing a counterclockwise torque. If this is going to sub to 0, then you can solve for x because that's your only unknown, and bam, you can get exactly where that's going to be. All right, so that is a recap of the things we did in class today. Then you guys had some time at the end to work through these problems yourself, help each other out, ask me questions, and yeah, so that is a wrap on this week.